Let's now do a proof of the polynomial remainder theorem. And just to make the proof a little bit tangible, I'm going to start with the example that we saw in the video that introduced the polynomial remainder theorem. We saw that if you took 3x squared minus 4x plus 7 and you divided by x minus 1, you got 3x minus 1 with a remainder of 6. And when we do polynomial long division, how do we know when we got to our remainder? Well, when we get to an expression that has a lower degree than the thing that is the divisor, the thing that we're dividing into the other thing. And so in this example, we could have rewritten what we just did right over here as our f of x. Let me just write it right over here. So we could have said 3x squared minus 4x plus 7 is equal to x minus 1 times the quotient right over here, or you could say the quotient times x minus 1. So it's going to be equal to this business. It's going to be equal to 3x minus 1 times the divisor times x minus 1, and then you're still going to, and this isn't going to, when you multiply these two things, you're not going to get exactly this. You still have to add the remainder. So plus the remainder. And actually, let me write the actual remainder down. So plus 6. And the analogy here is exactly the analogy to when you did traditional division. If I were to say, actually, let me just show you the analogy. If I were to say 25 divided by 4, you would say, okay, well, 4 goes into 25 6 times. 6 times 4 is 24. You would subtract, and then you would get a remainder. You would get a remainder 1. Or another way of saying this is you could say that 25 is equal to 6 times 4 is equal to 6 times 4 plus 1. And so we just did the exact same thing here, but we just did it with expressions. And so, once again, I haven't started the proof yet. I just wanted to make you feel comfortable with what I just wrote right over here. If I divided this expression into this polynomial, and I were to get this quotient, that's the same thing as saying this polynomial could be equal to 3x minus 1 times x minus 1 plus 6. Now, this is true in general. Let's subtract a little bit. This is our f of x. So that is f of x. So f of x is going to be equal to whatever the quotient is, and let me call that q of x. So just in a different color. So I'm going to call that q of x. This right over here is q of x. So f of x is going to be equal to the quotient q of x times, this is our x minus a. It's, in this case, a is 1, but I'm just trying to generalize it a little bit. So x minus a, and then plus the remainder. And we know that the remainder is going to be a constant because the remainder is going to have a lower degree than x minus a, and x minus a is first degree. So this, in order to have a lower degree, this has to be 0th degree. This has to be a constant. So this is true in general. This is true for any polynomial f of x divided by any x minus a. So this is just true. So this is true for any f of x and x minus a. Now, what is going to happen if we evaluate f of a? Well, if f of x is indeed can be written like this, well, we could write f of, let me do a in a new color so it sticks out. We could write f of a would be equal to q of a. So q of a times, I think you might see where this is going, times a minus a times a minus a plus r. Well, what's that going to be equal to? What's all this business going to be equal to? Well, a minus a is 0. So, and q of a, I don't care what q of a is. If you're going to multiply it by 0, all of this is going to be 0. So f of a f of a is going to be equal to r. And so you're done. This is the proof of the polynomial remainder theorem. Any function, if when you divide it by x minus a, you get the quotient q of x and the remainder r, it can then be written in this way. And if it's written in this way and you evaluate it at f of a and you put the a over here, you're going to see that f of a is going to be whatever that remainder was. And that is the polynomial remainder theorem. And we're done. One of the simpler proofs that exist for something that at first seems somewhat magical.